So we'll start the today's sessions, lecture number 4 on single view and multi-view geometry. So now over to Samarth.
Yes, thank you, Bhupendra sir, and I'm just sharing my screen. Yes. All right, yes, so welcome everybody, and I hope you can see the slides. And I did not release the homework last time because there were some things that I could not cover, but I'm hoping to cover them in today's lecture, and then in addition to some other things which will help you understand these topics better, and then I will release the homework. So hopefully you'll find the homework more interesting and easier to finish. So let's get started. And as always, just whenever you have questions, type in the chat box or unmute yourself and ask the question. If you have any questions right now about last lecture, you can also ask. But if not, I'll just continue with today's lecture. Just to recap very quickly what we discussed last time, we saw again the projection equation, which is x, the pixel coordinates in homogeneous coordinates, is a homogeneous coordinate equivalent to our intrinsics matrix, rotation, translation, and the 3D point. And we said that this is called P matrix, which is 3 by 4, and it is a projection matrix. So you can also write x is homogeneously equals P times x. And then we spent most of the last lecture discussing the special case where our points, 3D points x, all of them, they lie on a plane in the 3D world. And we saw how if that is the case, then this P matrix actually becomes a 3 by 3 matrix, and we said that is a homography matrix, H. And since all those 3D points X lie on a plane, we can ignore their Z coordinate and we can write these as small x. You can say small x dash. So now this homography matrix is 3 by 3, and this is 3 by 1. This is also 3 by 1. And then we discussed the way to solve this H matrix, basically get the 9 elements of this H matrix. If we have some image readings, for example, in an image, if we take an image of a plane, for example, if you print a chessboard on a page of paper and take a photo of it, and then you detect the corners of that black and white chessboard. So those are corners detected in our image. And then on the chessboard itself, we have the coordinates in the plane of that chessboard. So if we have those kinds of corresponding pairs of points, then we can use them to solve for this H matrix. So that was what we discussed last time, and I felt that last lecture was a little bit more heavy on the mathematics side of it. All of it is quite necessary, but I think in this lecture I'm going to try and provide a bigger overview of why that is necessary and some other more practically understandable applications of that. So let me start with the basics about this branch of computer vision that we are discussing here. It's called 3D geometry, or single view and multi-view geometry. There are various names for it, but the basic idea that we want to explore here is that the camera should be treated as a sensor, and actually it is a sensor, right? Just like how a voltmeter or ammeter, it measures current, the camera is a sensor which measures the 3D world that's in front of the camera. And the whole point of all this single and multi-view geometry is to develop some theories about if we are seeing some readings in our sensor, in our camera sensor, then what does that mean in the real world? So in our case, the camera reading is an image, right? So if we see a particular image, what can we infer from that image about what is going on in the real 3D world? And an extension of that is, if we see some change in our image, like some point moves from one location to another when we move the camera, then what does that mean in the real world? Does that mean how many centimeters has the camera moved, or how big is the object so that it appears 5 pixels long in our image, and how fast is the car moving so that it moves 5 pixels from one frame to another inside our image. So those are all the various questions that this field tries to answer. So with that background, let's again start with our famous projection image, because we keep continuing to come back to it. And let me just first start to draw that image. So here again we have our image plane, and like always we have our camera center, and as I mentioned, the x-axis usually goes to the right, y-axis goes down, and then your z-axis typically goes out of the camera, right? So this is your z-axis, and the point where this z-axis intersects my image is called my cx, cy, which are part of my intrinsic matrix. Again, when you store the image in NumPy or something like that, its coordinate system will start like this. So we will say this is the u-axis and this is the v-axis. And the distance between this camera center C and this image plane is the focal length of the camera. So I will just denote that like actually, yeah, I will just denote that sort of like this. You can understand that in 3D. So that is the focal length. But since I'm drawing it in 2D, I'm just drawing one focal, but you can imagine that there is a there could be a different focal length along x-axis and different focal length along y-axis. Now, when we have a point P in the 3D world, this point P is measured with respect to the origin, which is our camera center. So then let's imagine that this point P is actually in the xz plane. So this xz plane. So its y coordinate will be 0, and then its projection along the z axis. So this will be its x coordinate, right? And similarly, this will be its z coordinate. Now, when we project this point, let's see what happens. So that ray again intersects the image plane at a point which we call u comma v. All right. So this is the whole picture, which I'm sure all of you are quite familiar with by now. But I want to highlight some points about this picture. And let me just kind of draw a thing. So as I said before, this whole field is about deriving various kinds of information from our image observation. So in the image, we see this pixel u comma v, right? And then there are 3 different quantities. One is the intrinsic matrix of the camera, which includes the focal length and the cx, cy. And then there is the z coordinate of this point P, which I will call z and then superscript c to indicate that it is measured with respect to this camera coordinate c. So I'll put a c here as well. And then there is the x and y coordinate of this point P. And the idea is there are these three different quantities. All of them are interconnected. And you need two of them to derive the third one. So if you have intrinsic matrix and the distance from the camera, then you can derive x and y and so on. You can move around in the circle. And you always, of course, you always need to have your image observation. So when we think about our camera as a sensor, and when I mention calibrating your camera, that basically means deriving a function which says that if my 3D world looks something like this, then it will generate a particular kind of reading in my sensor. And we saw how the calibration of a single camera mainly involves this K matrix, which is focal length and this CXCY, which is called principal point. So the idea is if we have this Z coordinates and X and Y coordinates, then we can derive this intrinsic matrix. That is, we can calibrate our camera. So let's just look very quickly at how hypothetically we can do that, right? So calibrating a camera. So starting with some hypothetical case. What is this hypothetical case? It is basically that we have our camera here, and then let's say we have some 3D object, just like we drew last time, this mug here. And we know exactly, so we have this, again, this camera, and we have this point P, right? So these are all XC, YC, ZC. We know exactly this point on the mug, and we know where it projects. So U comma V to the image. So what can we do? Basically, we write our projection equation, which is you have U dash, V dash, and W. So since I put a W here, I can write equality, right? Then you have your Fx 0Cx. This is your intrinsic matrix, right? And again, so this mug will have its own coordinate system. Let's say this is its own coordinate system. And so this coordinate system is O, for example. So let's say that right now we know exactly the transformation between this camera coordinate system and this object's coordinate system, right? Which we will denote as this CTO. We already saw this. And so then the idea is, if we know this point, if we, for example, if we have a 3D model of this mug, and we know these points XO, YO, ZO in the object coordinate system, then using this matrix, we can transform them into this XC, YC, ZC, which are the camera's coordinate system, right? So in our projection equation, we will write sort of like this, which is the rotation and the translation. Both of these are the first three rows of this CTO matrix, right? And then we have our XO, YO, ZO, and 1. So let's say we do this matrix vector multiplication. And so here we get U dash, V dash, W, and we get XC, YC, ZC, right? Because these matrices will transform from the object coordinate system to the camera coordinate system. So then we can write down various equations from this, which are U dash equals sorry, plus CX ZC V dash equals FY YC plus CY ZC and W equals ZC. And then we said if we want to convert these homogeneous coordinates into actual pixel location, then we need to divide, then we need a 1 over here. So that means we need to divide this whole vector by W. So then we get finally our pixel locations, which are actually U equals Fx XC by ZC plus CX, and V equals Fy YC divided by ZC plus CY. Yeah, so we have these equations. Now, what are the unknown quantities here? We want to calibrate the camera. So our unknown quantities are this Fx, Fy, and Cx, Cy, right? So definitely, I think now these are basically a set of two linear equations which are basically linear in the unknown variables, right? So now we have 4 unknown variables, and so just these two equations will not be enough to solve for them. So what we do is we take more points on the mug. So let's say we know this point, this other point, and then we project all of them and create more such kind of equations, and then we solve them. So we solve the linear equations and we get the camera calibration parameters. So we have calibrated our camera. But this, as I mentioned, is a hypothetical case because this is almost never possible in the real world. Why? Because first of all, it is really difficult to know this transformation matrix exactly, right? Even if you have a mug in the real world, like for example this mug, and if you have an exact 3D model of the mug which you can use to get these right, which you can use to get all these points. Imagine when you take a photograph of a mug, you don't know exactly to the last centimeter how far your camera it is from that mug, and actually it's inside the camera. It's really hard to measure where the sensor of the camera is, right? Because you have this kind of big camera box around it. So, and another big problem also is it is really difficult to know that, let's say now you have this mug and you have sort of an image of the mug formed in your image. It is really difficult to know that this point on the image corresponds exactly to this point on the mug, and this point corresponds to this point on the mug. Those are, difficult problems on which machine learning research is being done even right now. So this is called the problem of correspondence between 2D point and 3D point. So because of these two problems, usually when people want to calibrate their camera, what they use is a chessboard, like what we saw last time. So let me see. Calibrate camera using a chessboard. Now, we saw last time that, well, let's see. So there are these two different problems. Let's see how the chessboard solves both of these problems. The first problem about this correspondence problem. So here I'm showing you, let's see. Yeah, here I'm showing you an image of a chessboard that I took. You can actually visit this website that I've mentioned in blue here. And that website, you can easily generate PDFs of different kinds of chessboards and things like that. And it's really cool to check out that website. So you just generate the PDF, print it out, and you have the chessboard pattern that you want. And then there are various programs in Python, C++, everywhere, which will detect the corners. So here I'm showing you those detected corners, and they usually detect the corners very reliably. So you're like, I'm showing you those corners here. And what does this mean? This means that we have solved the correspondence problem, because we know that on the chessboard, let's see if this, yeah, so this annotation works. So on the chessboard, we know, for example, that we can say this is x-axis, y-axis, and the z-axis comes out, right? And so if we have measured this, let's say this is 5 millimeters or something, then we know exactly the coordinate of this point. We know exactly the coordinate of this point in the chessboard's coordinate system, which are going to be XO, YO, ZO. And this ZO is always going to be equal to 0, because this is a plane. But since we have these algorithms to detect the corners, we also know exactly where those corners are in the image. So we have solved the correspondence problem. And what was the other problem? Yeah, the other problem was that we don't know this transformation matrix. So now what we saw last time was that if you start from this general projection equation like this, if your object is actually a plane, then this becomes sort of this homogeneous matrix x dash h. So that means both the intrinsic matrix K and the rotation and translation have both of them been combined into this H matrix right here. And we saw how to get the value of this H matrix. So now the problem is, if we know the H matrix, how do we know the value of this rotation and translation? Because that is the problem of getting this transformation matrix. And actually, I'm not going to go into the mathematical details of that in this lecture, but it is actually possible. You can actually read this paper. I will send you this paper afterwards, but this is a very famous paper. I think maybe from 2000, sometime in 2000. But yeah, this is the name of the paper: Flexible New Technique for Camera Calibration. And it goes into all the details about, there's this homography between the model plane, which is the chessboard plane, and its image. And then there is some solution about how to get the rotation and translation from this H matrix. So I'll send that link after the lecture, and I encourage all of you to read that paper. It's not very difficult, just some linear algebra. But instead, what I want to focus today is what we talked about last time, that if your object is a plane, then you have this equation. And we know what this means is that this x is equal to any constant c times h x dash, because if we remove this homogeneous sign here. So now this is a vector, this is a vector, and we know that when some vector a is some scalar c times some vector b, what that means is A cross B will be the zero vector, right? So then we said this X cross H X dash, let me just write vectors here, that also becomes zero vector. And this is where we started the whole mathematical derivation in the last lecture. So I would encourage all of you to, like when you are reviewing this lecture, when you reach this point, then you go back to the last lecture and follow the whole mathematical derivation. So that will actually help you to understand that mathematical derivation in the context of this camera calibration, right? And when you have understood that mathematical derivation to get this H matrix, then you can read that paper to understand how to get the rotation and translation. Now, let me actually show you what happens if you have managed to calibrate your camera. So again, when we calibrate the camera, that means we know its intrinsics K. So what K does is it allows you to project various things into your image. It allows you to project various 3D objects which are out there in the world into your image. And that is really useful for augmented reality, which I'm sure all of you know about. The most famous example is Microsoft HoloLens or Google Glass, or various companies are making these augmented reality devices, which is different from virtual reality. In augmented reality, you actually have a transparent glass, but there is some display technology which allows it to project various things onto the transparent glass. And that is quite useful technology. So let me just show you a quick video of how people are using that. So here's a video of somebody using it in a medical setting, right? So let me just skip ahead. Yeah, exactly. So they are wearing these augmented reality glasses and they're teaching these medical students about various anatomical features in the human body, sort of like this. But what this means is when they are, yeah. Oh, sorry. So the person is actually wearing the glasses, and that person is moving this device over here, and it knows the movement of the device through various other tracking technologies. And so then it means that inside their instruction module, they know that the 3D model of the various organ looks like this. It has various shapes that you can see and colors and things like that. And they know that if my device, sonography or whatever device, is pointing in this direction, then uh, the organs, intestines and stuff like that will be in this location with respect to my probe. Then uh, since they have calibrated the camera of the augmented reality device, so actually in the augmented reality device, the camera is actually your eyes, right? So they've calibrated the whole system that allows them to project this 3D model of the various organs into the glasses, so that when you see those glasses, those organs seem to be at that particular location because they are being projected using a particular transformation matrix and the calibration matrix. So this is roughly what is going on. There are various complications. This is a very simplified picture that I presented you. But ultimately, that's what's happening in augmented reality. So we saw briefly about how to calibrate the camera, and let's basically sort of draw that circle again. Now, people employ various tricks in order to derive various quantities from this circle. So let me talk about one particular trick. Let's say you have these image observations of some points and you have calibrated your camera as well. But what if you don't know either the X and Y or the Z? So then one very common trick that people use is taking multiple views of the same object. So that is called multi-view geometry. And the most famous example of that is whenever you go to see 3D movies, right? So they give you those glasses, and actually on the screen they are showing you two different images that are filtered by the two different glasses, and those two images are shifted just the right amount so that it seems like 3D to you. So let me just show you very quickly how that happens. So we will have two different cameras now, and actually let me scroll a little bit, and because I need some space. Yeah, so we have two different cameras with these coordinate systems C and C dash. And I will finish this figure later, but right now, let's imagine that we are looking at these two cameras from the top view. So if you're looking at them from the top view, the image planes are just these lines, right? And we have our so there is our x-axis, y-axis is actually going into the plane of the iPad, and the z-axis is coming out from the camera, just like how the z-axis comes out like this. X, Y, X, Y. So let's say you are looking at, both of these cameras are looking at one point in the 3D world in front of them. So then we draw this line here, we draw this line here, and this is the image of that point. And let's say that same point actually moves farther away. So then its image shifts, right? Let me just draw the straight line. Yeah. So then its image shifts. And what does that mean? So, you know, in the image, let's say this is the x-axis, right? And so this is 0 over here, this is 0 over here. So when the object was nearby, let's say this is z1 distance along the z-axis, then we had this x1 and x1 dash. I'll just give it some random values. So this is positive direction, so let's say this was 10, this is negative direction, this was minus 10. So the difference was 20 between these two. Now, when the object went farther away at a distance z2, then we see that these coordinates become smaller. So let's say this is 2 and this is minus 2. So I'm talking about this coordinate here, this inner coordinate. So now actually the difference shrinks to 4. And this difference is called the disparity. And the disparity happens because both the cameras are looking at the same point, but since the cameras themselves are shifted, the image of that same point in the image, the location of that same point in the image captured by these two cameras is different, and it is shifted. So, and we saw that the bigger the shift, the closer the object is. So actually you can see that very quickly just using your own eyes. You can take a pen and bring it in front of your eyes and close one eye after the other, and it will appear as if the pen is shifting to you. And then similarly, if you look at a far away object and then you do the same thing, the shift will be less. So that is the basic concept of disparity. And so then the idea is, if you somehow create a picture where let's say you create a picture where you're trying to draw a mug, but in 3D. You actually draw two mugs shifted by a little bit. Let me use the color that I have. So actually one of them will use red, the other one will use blue. So these are both the same mugs but shifted. And then the idea is you view them with glasses which have different colors, different filters. So this glass only allows the red glass. Let's see, how does that work? If the red, basically one of these glasses only allows one image to go through and the other glass only allows the other image to go through. And so your left eye and your right eye both see the image, but with some shift between them. And the shift is engineered to be proportional to however far away they want the mug to appear to be. So this whole thing is called stereo, and here is a quick example of that. So you must have seen all these videos where people, you can find lots of them on YouTube also, where there's a red image and a blue image, and then if you view it from these glasses, then it will appear in 3D to you. So the stereo problem is actually quite interesting, and let us go back to this image in the full 3D view. So now the idea is, here we assume that, for example, here we assume that we knew that both this point as well as this point corresponds to this point. So we know that these points and these points are actually the same 3D point. But in the real world, if you have two cameras, then you don't know which pixel in the left camera corresponds to which pixel in the right camera, right? So let's say there is some, again, mug we are looking at, and there's this point here, and this is its UV. Now, how do we search for the matching point in the right image? If we know the matching point, then we can measure that shift, and from that we can derive the distance to the mug. So like, actually I'm drawing the mug here, but the actual problem is to derive the position of the mug, basically, because we don't know the position of the mug. All we can see is the image of the mug, and we see another image of the mug here. So then if we see this point, how do we know which exact point it is on this image? One way to do, so this is where machine learning and all the other side of computer vision comes in, which looks at various convolutional features, gradient features, and things like that. But There is one very nice trick that we can also use. I think we saw in the last lecture, for example, that if we have one point here and we don't know the actual distance to the camera, so again, this point is unknown to us. As we move, as we move along this ray, it will project to sort of different locations, right? It will project to this whole line in this image. Just this one point, if you carry forward this ray, we know that the whole ray projects to this line here. So then if we want to find the matching point for this one, we don't need to search in the entire right image. All we need to do is we need to search along this line, right? And we know for sure that the matching point will be somewhere on this line. And then of course we can use the pixel values and the color and the neighboring pixel values and things like that to find the exact matching. But the search space is reduced from the whole image to just this one line. Now, how do we actually derive the equation of this line? First of all, this line is called the epipolar line. Epipolar line. And I'm not going to go into the mathematical derivation of the equation of this line. If you are interested, you can just post in the Google group, and I will share some resources there about the mathematical derivation. But the idea is, if you know the transformation between these two cameras, if you know the rotation and translation, then from this pixel location you can derive the equation of this epipolar line, right? So this is some trick that we have used to kind of cheat in this circle. So here we say that we know the image observation. So like we know this image observation in this left image, and we know the intrinsics because we can get this ray only if we know the intrinsics, right? Because we need the, I think we saw in the last lecture how we can use the intrinsics, Cx, Cy, and then the focal length, things like that, to actually get this ray. And in the case of a stereo camera, the calibration also involves getting this rotation and translation, which you can do again with chessboard, but that again is more complicated maths, so I will not go into that right now. But if you have calibrated your system, and if you know this, then you can actually use this kind of geometry tricks and search for the matching point using machine learning or some other technique. And then you can actually get these 3D coordinates, right? Because once you have established that this point corresponds to this point, then all you need to do is you measure the shift. So like again, this one is also lying on the epipolar line corresponding to this point. And so along the epipolar lines, you measure how much the shift has happened from left to right. And from that, you can actually derive that the distance is actually this distance. So that is called triangulation. And again, there are lots of tutorials on the internet about this, but I'm just showing you the basic concept that you can use this shift between left and right to derive the 3D coordinates of the point. All right. So then let me move on to the next set of problems. The next problem is called object pose estimation. What does that mean? So that means, again, you have your image, you have your camera center C, and let's say you have 3D model of a mug somewhere in your computer, and you have the exact, you have 3D printed that mug using that 3D model. So you have the same mug in the real world. And you've taken a picture of that mug. So now let's say you have this thing here. Now, this problem says if we know this picture of the mug, and we know that this picture actually corresponds to this 3D model over here, can we actually know the position and everything? Can we actually know the position of the mug in the real world with respect to my camera? So actually, the real mug in the 3D world will be like somewhere like this, right? And its image will be formed here. So then the idea becomes that, let's say we know some correspondences. Let's say we know that, this corner here is this edge of the mug. So we know in the 3D model that this thing here, and then maybe uh, there is some kind of pattern, like um, there's some kind of like a flower pattern or something like that on the mug, and we recognize that pattern. So for example, we know that the center of the flower is going to be the center of the flower here, and then we know, for example, that this point on the handle is again this point on the handle, and we know some other such correspondences like this. So these are called 2D, 3D correspondence. That means we know that this image point is actually this point on the mug, and that is again a big area in machine learning and everything, that if you train your algorithm using images of a particular object, then someone gives you a new image, can you identify various points on this mug? Those are called key points, and say that this point is actually this point is actually that point. Now let's say we have trained our machine learning and we know that. Can we use this information somehow to know the real position of the mug? So then the idea is we have calibrated the camera. So like we know this calibration and we know this image observations. So then using that, we draw the rays. Right? So we draw a ray from here. Um, I actually use the colors I have. So that it's easy to understand. Right? So we know these rays, but the mug can actually be at any particular distance, from the camera. So it could either be a big mug which is far away, and a small mug which is nearby. Both of them will result in the same image size, right? You can imagine that because it's being projected. A big mug far away is the same as small mug nearby. But if we have many correspondences, and especially if we have this kind of correspondences from multiple different viewpoints, like there's one image looking at the mug from this direction, another image looking from this direction, and we have these 2D 3D correspondence in all of them, then using this object pose estimation, there's all this trigonometry about that as well. We can actually know that the mug is at this particular distance from the camera. And that is actually also a very important problem in the real world, because, for example, I think we saw that in the first lecture, right? For example, if we are trying to land this spacecraft, right? So there's a camera looking down from the spacecraft on the surface, and it already has a 3D model of the surface of the moon. So here the equivalent is the 3D model of the mug. We know from the camera image that this valley that I'm observing corresponds to this point on the map. This mountain peak is this point on the map, and things like that. So then from that information, if we can actually know how far away the surface is, how far away that mountain peak and valley and everything is, then we know how to control the spacecraft speed and things like that. That's a very simple example, but this kind of thing is used in lots of other applications as well. Now, the final idea that I want to discuss today is, let's say you have some algorithm that does this object pose estimation. How would you actually check, right? How would you actually check that some particular pose that you got? By pose, I mean this rotation and translation. So like that collectively, that is called pose. How will you check that this pose is correct? One way to check is to take another image from another direction, right? So then we took this another image from another direction, and of course the mug will look different, but there is some overlap, like both of them are seeing this surface of the mug. So then the idea is, if we know this, if we know the motion of the camera from this image to that image correctly, then if our mug position is correct, then if we take this point on the mug, and do the projection, then it should actually come to this point in this image. If we take this point, it should actually project to this point in the image, right? And if the mug location were actually wrongly guessed, then the mug here would be drawn at a different location, and there would be some kind of error that we can measure. So this whole process is called reprojection. What this means is, we went from one image to the 3D object, and then we projected this 3D object to another image. So there is a reprojection, and then we check that the reprojection actually agrees, because in this image also we see the mug, and we see the various points on the mug. So that is one way to kind of check the correctness of that object pose estimation. And so that brings me to the homework, where the homework is kind of a very simplified version of this, because we don't have any mugs, we don't have any algorithms to detect various key points on the mug and things like that. But what I'm doing in the homework is I'm using the shortcut of the chessboard, because on the chessboard, first of all, it's a very simple object. So it's a planar object. And another thing is, we know exactly which corner corresponds to which corner on the chessboard, because we have solved that correspondence problem. So this is basically the homework. So there is a particular chessboard. It is lying on the world somewhere. And I'm giving you two images of that chessboard from two different viewpoints. And like in these images also, you'll see the image of the chessboard, lying like that. And we know for sure exactly that, for example, this point corresponds to this point here, and that corresponds to this point here. So to give you practice in terms of doing all these 3D geometry and things like that, what the homework says is that in this image 2 and this image 1, you actually have to do a copy paste operation. So you have to copy the pixels corresponding to just the chessboard from this first image and put them at the appropriate location in the second image. And the appropriate location is hard, because let's look at the two images. So, here there is, maybe this is pixel number, there's pixel number like 2040 something, this one. But the same corner here is maybe something like 1023. So how do you know? And that is where all these homography things that we learned comes into the picture. So using all the theory that we have learned, what I want you to do in the homework is that you can use this, you can use and I will give you the locations of each corner as a NumPy array. And then I will also give you the locations of the same points on the actual chessboard coordinate system. So there's like X, Y, 0, right? Each point will be some X, Y, 0. So using these two pairs, you first calculate this homography. Let's call this homography, let's call this homography 1H, or sorry, and just to match the homework, I will say A and B. So this is image A, image B. So this homography connects this to this. And similarly, from the other image, you can get another homography which connects B to C. What this means is that you have some point in the chessboard, like this point. You multiply that by this homography here. It will give you the location in the image A, and similarly for image B. And now, since both of these are 3x3 matrices, you can actually get the homography from A to B, which is going to be AHC and then BHC inverse, right? Because what this means is AHC, CHB, these two things cancel and you get AHB. So that is the idea, because if you have that, then you will you'll be able to transform a point in the image B using this one, and you will get the point in the image A. And similarly in the reverse direction. So then what you can do is you can basically go through each pixel here. Like let's say you're at this pixel. Or actually, since this is the equation, we actually have to go through pixels in image B. So let's say we have this pixel, then we take we transform it by this matrix, then we get this pixel in the image A. So then we take the color value from this pixel and put it here. Similarly, each and every point will be transferred like that, right? And so then you have basically copy pasted this chessboard from image B into the chessboard from image A. And then you can similarly do the reverse. So let me just quickly show you the final expected result of this. Yeah, I think this is better visible. So this is this image over here. So I will quickly change the two images and see if you can spot the difference. Do you see the difference? So in this, the rectangular area at the center is actually, if you see closely, it's a different shading, because that shading is because it is being taken from that chessboard is being taken from the other image. And similarly here, you see the difference? There's a different shading because those pixels are coming from this image, which has a different shading. So don't worry, most of the code actually I have written. You just have to write the code for calculating this homography matrix. So calculating this homography matrix from the image to the chessboard, and then the same code will be reused to calculate homography matrix from this image to the chessboard, right? And then it will then do all this derivation and then actually do the copy pasting. So I will do all that. You only have to write the code for getting this homography matrix, which we learned in the last lecture with that direct linear transformation algorithm. So I will very quickly just mention one last point and then end the lecture. There is one trick that you use when you are actually copy pasting colors. So let's say you have two images, and then I will actually kind of, so these are not chessboard now, there's actually, imagine these are pixels. Okay, and let's say that you derived whatever homography matrix and things like that, and then you want to transfer the color from the left image to the right image. So what can happen is the pixel coordinates are actually integers. Like this is 0 0 here. This is 1 2 3. This is 4 0. This is 6 0 and things like that. But the homography matrix are actually real numbers. So when you multiply this integer by a real number, you're actually going to get another real number. So it might be possible that, let's say you took this pixel and you multiplied by this homography and you found that it actually goes to some value here, in terms of the real number. And then the next pixel here, it goes to some value here in terms of the real number. And typically when you want to copy the color, so like each pixel has a red, green, blue value, so you need to set the red, green, blue value of this pixel using the red, green, blue value of this pixel, what you do is you take this coordinate and round it off so that you convert the real number to the floating point. Real number to the integer. So then you get the actual pixel value, and then you just assign the variable like that. But because of these rounding things, it might be possible that when you're copying each and every pixel from this image, some pixels here are going to be missed out because of this rounding, right? And so there is a trick that people use. So let's say we want to create a picture in this image B. Instead of looping through the pixels in this image A and going from A to B, what people do is people take the inverse of this H matrix and loop through each pixel in this B image. So like for this B image, they will go here, round it off and take the color value there and put it at this one. Then for this one, they'll go here, round it off, take the color value here and put it here. So then there's no question of missing any particular pixel in this B image, because when you go from B to A, or where even if you round it off, you're actually going to be at some pixel, right? And you can take that pixel's value. So that is called actually inverse warping. And this homework uses inverse warping, but I've already done that for you. So you just have to derive the H matrix and the rest of it will be completed. So yeah, with that, I think I will end today's lecture. If anybody has any questions, I can spend some time answering questions, or if not, I will end the lecture and then release the homework in 1 or 2 hours.